Okay, so now we're just doing as many electrophilic aromatic substitution reactions as we can remember. All right, so they kind of fit into three nice little categories. The first one being like a halogenation. So what's the other halogen that we know how to stick on a benzene ring?
Chlorine.
Chlorine, yep. There are these like acid catalyzed ones where we're putting on which two groups?
Or the
Yep.
NO2, and then
Nitro group. It's like a sulfonyl group. Okay, and then these ones were these, oh my God, what are their names? Friedel-Crafts type reactions where we're actually making new carbon-carbon bonds. So the first one would be just putting on any old alkyl group. And then what group did the next one, the last one, put on?
The cyano group or whatever it was.
No, it's not a cyano group. This one's actually an acyl group that we know how to put on there. We know how to swap out a we just learned last chapter that if you did like this, I think you're thinking of the diazonium salts. We know how to do a substitution reaction for a cyano group. But in this chapter, in terms of these are specifically electrophilic aromatic substitution reactions starting just with benzene, right? Not anything that has a fantastic leaving group. Okay, and so this would be an acyl group, right? Again, this is like one of the names that we don't really use all that much, but it's important to remember just in case they throw it at you. Acyl is essentially something that contains a carbonyl. Okay, and if you kind of remember back, the mechanism for all of these is essentially identical. You have benzene acting as what in each of these reactions, the nucleophile or the electrophile?
The nucleophile, right?
So the nucleophile, so it's that pi bond in the benzene reaching out and knocking. The weird thing is that we needed some fancy catalysts in order to get all of these reactions done because benzene by itself is a pretty crappy nucleophile, right? So let's see if we can't go in and annotate these with the different catalysts that we would have to use for these reactions. So everybody take a second and see if you can't fill in our wheel here with what catalysts we would need. All right. So, I mean, if you guys haven't noticed by now, I'm all about like trying to group things in my mind that are very similar. Four of these actually have very similar catalysts that we're going to use. Okay. And that is so for the chlorine, for example, aluminum chloride, right? You just need chlorine gas and aluminum chloride. Aluminum chloride is also used to catalyze our Friedel-Crafts type reactions. Okay, for putting on the acyl group, we'd start with an acyl chloride. Well, that's not going to work. For putting on an alkyl group, we would start with an alkyl chloride. And then the bromine, we can kind of throw in a similar category because we can use, instead of aluminum chloride, aluminum bromide. Okay, so those are all sort of very similar kind of catalysts in terms of like grouping things in your mind. Just an aside, another one that we learned about for bromine in particular was you can use iron. All right, and then these acid catalyzed ones, you can also kind of throw same place in your mind because they're all going to be acid catalyzed. What's our favorite acid catalyst that we freaking seem to use all the time? H2so4. For the nitration, you're going to have nitric acid in there as well. And then for the sulfonation, you use fuming H2so4. Okay. Now the last, again, just talking about monosubstituted benzenes using this particular reaction, the last thing that we sort of learned was that because you have to have these catalyzed type reactions, what the catalyst is really doing is making your electrophile into a way better electrophile, because again, benzene is not a great nucleophile. So let's see if we can't remember what the electrophilic species in each of these reactions would be. Actually, let's do chlorine because that's the one that's similar to a lot of the other ones, right? So remember we had this thing where first the catalyst is going to change our electrophile into a particular electrophilic species that's going to be attacked by the bromine or by the benzene. So let's see if we can't remember what that would look like in these three cases. So this is AlCl3. What is that doing for us? What's the sulfuric acid doing for us in the nitration? And what is fuming H2so4 doing for us? What are those different electrophilic species going to be? Okay, so the aluminum chloride, remember what that does is it actually just bind to that Cl2, right? Sort of forms this complicated looking complex. And then of course we need charges. So just to balance everything out, this would be the electrophilic species in this case. And this is very, very similar to the Friedel-Crafts type reactions as well, where your acyl chloride or your alkyl chloride is doing the same thing. It's forming this type of complex with the aluminum chloride. What about the nitration reaction? What does that guy look like? Our electrophilic species. Oh, well, first of all, that's not a 3. That's a 2. And that's a really good clue as to what it's going to look like here. NO2, that's exactly what our electrophilic species is. What's the only thing missing from my structure that I have right here? Because my nitrogen has 4 bonds, it needs
Charge.
a positive charge. Yep. So remember, don't forget all this stuff that you learned about in general chemistry, right? Your formal charges, all that good stuff. And then what about the fuming H2so4? Remember, the fact that it was fuming meant that it was giving off this particular gas. And that is S. And again, you can kind of get the hint from what the group is here. One thing I want to note. So our book told us that it was this complex right here, SO3. Notice how you have this sulfur in the middle that's double bound to a bunch of electrophilic oxygens. So it's pulling that electron density away from that sulfur. Again, just making it a really good electrophile. So the first step that we learned about in our book was the ring attacks, knocks that pair of electrons up to the oxygen, and then it eventually will grab a hydrogen, giving us our group right here. I just want to say that I have seen books where the very first step is where the electrophilic species, instead of being SO3, it actually looks a lot like what our eventual substituted functional group is here. And you have something like this instead. Okay, so kind of, I've just seen it both ways. Who knows what's actually correct. Our book told us it's SO3, but I've also seen it as SO3H. So just keep that in mind when we're talking about, things that the ACS can throw at us. Okay. Cool. And then the last sort of big one that we learned about that sort of played an important role was something that we can do once we have nitrobenzene. And that is to turn it into aniline. Okay. When we first learned about it, we learned that it was going to be first like iron or zinc in acid, followed by a base. Then we got to the amines chapter and they threw a few more metals in there like tin and tin chloride. So let's just say anytime you see some metal in acid and then base condition, we can go ahead and assume that it will reduce that nitro group to a benzene. Rather than memorizing some list of possible metals, if you see some combination of metal, acid, and then base, let's just go ahead and assume that what that's doing is turning our nitro group into aniline, right, into an amine group. There was yet another way we learned about doing this in our last chapter, and that was just with H2 and palladium. What else does H2 and palladium do? Does anybody remember like when this was kind of first introduced to us?
It was adding hydrogens to double bond to.
Yeah, adding hydrogens to like pretty much anything other than benzene. So you can turn an alkene into an alkane. You can turn an alkyne into an alkane. But this combination of reagents should just be filed away as sticking hydrogens places, right? Reducing agent. H2 in palladium is just a strong reducing agent that we've seen kind of over and over again in our course. All right, so now for kind of the harder part here, let's take our our 6 groups. We'll just do 5 because bromine and chlorine are kind of lumped together. Oh, we can do aniline too. How about that? Okay, actually, I lied. One more thing I want to do before we jump on is to talk specifically about this type of Friedel-Crafts reaction, the alkylation reaction, right? So this is where we just take benzene and we have some sort of alkyl chloride in the presence of aluminum chloride. And again, that's going to sort of just put that alkyl group on that benzene ring, right? A substitution reaction. These reactions go through carbocation intermediates, which means that you have the possibility for a hydride shift. So remember that, you know, a secondary alkyl halide, fine, that's not going to do any sort of hydride shift. But if we had a primary alkyl halide, something like this, we would expect a hydride shift onto that secondary carbon. So actually both of these alkyl chlorides would end up giving us the same product because of that potential for a hydride shift, right? Methyl carbocations don't like to form. So in both of these cases, you would get this particular product. All right, so just something to sort of have as an asterisk in your mind, hydride shift may occur.
Do methyl shifts happen too?
Yeah, I don't see why not, yeah.
Okay.
So if you start that, I mean, you'd have a very specific, like that would be the only substrate that you would really have to worry about, right? But yes, there could be a methyl shift because it's only going to have the next door neighbor. Crap, I gotta sneeze. Okay. So now we got to get to di-substituted benzenes, right? So now we've undergone one round of electrophilic aromatic substitution. Now we're going to undergo another round. So let's just go. In all cases, we'll put another bromine on there. So everybody tell me what the product is going to be for this same sort of bromination reaction after we've already gone one round of electrophilic aromatic substitution.
Would it just add more bromines?
It's going to add a bromine, but the hard part here is where, right? You have.
Is it a meta addition?
Yeah, so that's what we have to know, is whether our current substituent is orthopara or meta-directing. Remember, we have all these different benzene substituents, and we were able to categorize them as being either orthopara or meta-directing. So see if you can't remember, out of all of our groups here, what's what. Actually, let's do one more just because it's similar.
Are we just adding one?
Yeah, just one. Right, my main goal is to get you guys to sort of refresh your memory as to what's orthopara and what's meta-directing.
Would it be a meta-directing?
So it's gonna, you know, for each one of these, it's gonna be a little bit different. So we'll go through sort of how to tell, but see if you can't do as many as possible. For each of them, we're gonna be adding a bromine. I just got lazy and I didn't want to write that 100 times. So for each of these, do a bromination reaction of the current benzene substituent. I will be right back. Okay, so bromine is going to be, I'm gonna like abbreviate here, orthopara. So in that case, you would expect it at either the ortho or pair position. Real quick, on our bromine here, let's just label what's what. Where's the ortho position?
108 or 1.
1, 2, 3. Yeah, so it's going to be ortho is 1. What about meta?
2.
Yeah, meta is going to be next. And then para is that one guy on the very opposite end. So remember OMP, like OMG, but OMP. That's how we're going to remember the order. Okay. All right. So yes. So bromine is orthopara. So I'm just going to stick it on the para position. It could go to the ortho position. You get a mixture. What about the nitro group?
That's meta.
That is meta. What about the amine group?
Orthopara.
So that one's orthopara. That there. That sulfonyl group.
I don't remember.
That one's meta.
It's meta.
Yep. Alkyl groups.
That's orthopara.
That is orthopara. This is the only time when you have something big and bulky like what I have on there now that you want to be thinking about sterics and put it in the para position primarily. It is any alkyl group is an orthopara director, but remember when it's big and bulky, it'll sort of occupy the space of that ortho group. So the major product will be in the para position. Okay, what about when we have benzaldehyde or a carbonyl group directly next to the ring?
Meta.
That is meta. Okay. And lastly, I sort of threw this one in at the end, so you might have missed it. This is when we have this ester. Where's that going to direct? Ooh.
Is it orthopara?
It is orthopara. All right, so now let's take stock of what we got here in terms of our directors. So I'm going to erase this just so it's bothering me how ugly this is. Okay, so we'll go through and label orthopara. So our bromine was orthopara. Nitro was meta. Aniline orthopara. Meta. Orthopara. Oh, look at that. On and off. Okay, so how do we tell? Like if we just want one simple rule of thumb that's going to let us know what's what, the easiest thing that I can do to sort of simplify for it is if you have a lone pair directly next to that benzene ring, such as we did with aniline, with bromine, with our ester group, right? And in particular, right, notice that our ester group is arranged in such a way that the oxygen is directly connected to the ring. If I stuck an ester onto this right here, it would still be meta. Okay, so if you have a lone pair directly next to the ring, it'll be an orthopara director. The only exception to that rule would be our alkyl group here that doesn't have any sort of a lone pair, but it's still an orthopara director. Okay, but that's sort of the simplest rule that I can give you guys for when you can expect something to be an orthopara director is if it has that lone pair. Remember, if it has that lone pair, it can donate those electrons to the ring. And that's really the root of orthopara directing versus meta directing, is whether you're electron donating or electron withdrawing. I don't want to spend time drawing all these resonance structures and all that business, but that's exactly how you can demonstrate that something is orthopara or meta directing. So it's a good idea to sort of review that in your notes. But yeah, any of these things with lone pairs, they can throw it into the ring, be electron donating. And so that's why they would be orthopara directing. Okay, everything that's meta directing is electron withdrawing, and that's what leads it to direct to the meta spot. But yeah, that's kind of the easiest short, fast rule I can give you. Okay, so real quick, in addition to, I want to move on to the next chapter here, so I'm going to go kind of fast. I do want to sort of refresh everybody's memory that in addition to being orthopara directing, that's kind of the first thing that you want to remember about these different groups. But we also, where's my little cheat sheet that I have? We also had classifiers as being strong, moderate, or weak. I might get rid of all this noise because it's not going to make any sense without the context of the lecture video. Okay, but just remember that in addition to classifying the, right, so first sort of order of things that we can worry about is whether or not they're orthopara or meta directing. Right, so if we're only going to remember one thing about these substituents, that's sort of the way to go. In addition, though, we had this sort of further classification as being strong, moderate, or weak. So when does that come into play? When do we have to worry about that? That's when we're going to be forming a tri-substituted benzene. So we have like competition between two substituents that are already there. That's when we have to worry about something like that. So let's just do a simple example real quick. And now I want to put on Oh crap, that's not a good example. Now I'm going to put on, I don't know, who cares? A sulfonyl group here. Now we have some conflict because bromine is what? Meta or orthopara?
Orthopair.
Orthopara. So that means that bromine wants to put it here, here, or here. Right? That's what bromine's going to direct to. But our nitro group is going to direct where?
To the meta position.
To the meta position. So our nitro group wants to put it there. So this is really this is why I'm sort of talking order of importance. Knowing strong, weak, all that good stuff is specific to this type of problem right here, where now I'm going to form a tri-substituted. And so I have a battle going on. Which one of these substituents is going to win?
The NRP.
Right? Yeah, so that's when this classification comes into play here. Notice that our bromine is a weak, it's actually a deactivator. That just means that it slows a reaction down compared to benzene. I don't know if I'd worry too much about that. I think importantly, the weak part, and then our nitro group is a strong deactivator. So we have weak directing one place, but strong directing the other place. Just like you'd expect in a wrestling match or something, it's the strong that wins. And so our final product here would direct it to the meta position and up to. And so that was what we would get for this reaction here. All right, so that's when all that strong, weak, moderate classification business comes into play. The last thing about this chapter I want to review, right? These were all EAS. What does the A stand for again? What is it? Aromatic, right? Electrophilic aromatic substitution reactions. Electrophilic because you're substituting for an electrophile on that benzene ring. We also learned about nucleophilic aromatic substitution reactions. Okay, this is like not as big of a focus of the chapter, but nonetheless, there were 3 rules that we needed for a compound to actually undergo nucleophilic aromatic substitution. Anybody give me one of them?
Good leaving group.
You need a good leaving group, yep. Which is in the context of what we've learned, pretty much exclusively going to be something like a halogen, right? A chlorine or a bromine. There's another really important thing. Remember that benzene previously played the role of an electrophile, right? So it was the one that was electron rich, reaching out and grabbing something else. For these, we need benzene to play the role of a nucleophile, which means that we need it to be electron poor. We need something pulling the electron density out of that ring. So we need a strong electron withdrawing group. Okay, so this is a super important rule for this type of reaction. The most common example is going to be a nitro group. If we look back out at our lecture, we actually saw like a few different examples. A nitro group, again, by far the most common. You can also have an ammonium salt, so a nitrogen with a positive charge, or something like CBr3. Okay, a chlorine that has a bunch of halogens on it. Those are the only 3 strong electron withdrawing groups that we know about. So you got to have one of those. And then importantly also is the orientation of these 2 groups has to be ortho-para. And then what would happen is if I took some nucleophile and reacted it with a compound that had all these three rules, you would just get a substitution of that nucleophile for that leaving group. Okay, so in this case, if I use sodium hydroxide or something like that, I would get that compound there. All right, and then the last one that I want to talk about is another type of mechanism that we learned. Let me see where it is. Okay. Something that we learned called a elimination addition reaction. These are very similar for the nucleophilic aromatic substitution reactions, except for you have a compound that it has a good leaving group, but it doesn't have your strong deactivator on there. Okay, so this instead will undergo something called elimination addition. And the bottom line there was that it goes through this very weird intermediate, benzene, where you actually have a triple bond on that benzene ring. Why was this important? Like, why would we ever need to worry about a compound that underwent this type of mechanism versus the other one? Is because you'll get a distribution of products. You'll get two different products, okay? So if I'm gonna start out with something, you know, if you started out with just chlorobenzene, it wouldn't matter because you don't have anything to compare it to. But if you started out with something with a methyl group on there as well, right? So it's not our strong deactivator. So it's not gonna go through the NAS type reaction. It's gonna instead go through this intermediate here. And why that matters is because your new nucleophile can be added to either carbon, right? So what's gonna happen is, I don't know, if we have some strong nucleophile there, we'll get a distribution of products. Oops, that's not a real thing. Okay, so these are both sort of nucleophilic substitution reactions. The difference is whether or not they have that good electron withdrawing group. If it doesn't, it'll go through this elimination addition type mechanism where we get a distribution of products. All right, crash course in everything that was chapter 18. So let's move on to aldehydes and ketones. What we got time was. Okay, aldehydes and ketones. Well, so first, come up with like 3 different ways that you can make an aldehyde from anything else. Just sort of pick your brain for, we know a ton of reactions at this point. Just pick your brain for various reactions that we can use that will come up with any sort of aldehyde or ketone. Anything you can think of.
To make an aldehyde or ketone?
To make an aldehyde or ketone, yes. So if we're preparing an aldehyde or ketone.
Or like oxidation reactions with like the chromium and H2so4?
Yeah, anything that you can think of. You can start with anything you want. Just kind of see if you can't pick your brain for, you know, there's so much out there that we've learned that sometimes, I don't know, it's good to just, without a practice problem or anything, just what can I come up with? Okay, so first, I just want to note that this particular set of lecture slides has a really good summary of everything we had done up until that point that would give you an aldehyde or a ketone. So just reviewing those, the big ones that I think I would point out just because I've seen them on the ACS before and I feel like they're reoccurring. If you have a primary alcohol, remember you need one of those softer oxidizers. You can't use the chromium-based ones. And so PCC is by far the most popular. If I had to make a bet as to which soft oxidizer was going to be on the ACS exam, I would say PCC. Okay, remember the difference between PCC and something stronger is something stronger when you have a primary alcohol would give you a carboxylic acid. PCC being softer will give you an aldehyde. It'll stop after adding that one oxidizer. All right, I'm not saying don't know the other ones, the DMP and the COCl2, but again, just if I was a betting man, PCC would be the one that I would think would show up on the ACS. Okay, it's like the classic one. DMP is like a newer, fancier one. One that we probably haven't thought about in a billion years is the ozonolysis of an alkene, right? So this is where you chop that alkene bond in half and stick two oxygens on there. Just while we're on this same sort of whatever, we also saw ozonolysis with regard to alkyne, and that gave us a different functional group. Does anybody remember? That would be a carboxylic acid. All right, so ozonolysis of an alkene gives you a ketone or aldehyde. Ozonolysis of an alkyne gives you a carboxylic acid. So I probably haven't thought about ozonolysis reactions in 100 years. We also had, so now we're getting into alkyne reactions, hydroborination, oxidation, give you an alkene, an aldehyde, right? So this would put the oxygen on that terminal carbon. You can do a very similar reaction with, You can do a very similar reaction with sulfuric acid, but that would put it on that second carbon, giving you a ketone instead of an aldehyde. So these are both starting with alkynes. All right, so these are all in the lecture notes. So I'm going to blaze through them just sort of to refresh everybody's memory. The other kind of big one, I don't know, again, just kind of thinking hierarchical, is oxidation of secondary alcohols. And then again, the key one there is this sodium dichromate, or again, hopefully I've gotten you at this point trained. Anytime you see chromium, you're thinking strong oxidizer. So in the case of a secondary alcohol, you'll just get a ketone. If you had a primary alcohol and these same set of reagents, again, that strong oxidizer would take it all the way to a carboxylic acid. And then the Friedel-Crafts acylation reaction is a way of making a very specific ketone or aldehyde where that carbonyl group is directly next to the ring. So that's kind of a, I don't know, fancy little, very specific type reaction. The other ones are more general. Since then, we've learned a few more that I just wanted to go over because they're not in that nice little list at the beginning of chapter 19. And that is, we know how to convert an acyl chloride into any ketone we want using the Gilman's reagent. Okay, so this is one that we learned after this chapter, so I'm just trying to add to that list. Remember, we're at the ACS exam now. We're at the multiple choice part of the course. So really, it's not about like having these things strictly memorized. It's being able to sort of sight recognize stuff because you'll have that multiple choice. So making yourself a reaction wheel for each functional group is a really great way to summarize that information. So again, you can start with those reactions that are listed at the beginning of chapter 19, and then you can add these guys to it because these are the ones that we've learned since. Okay. We also know how to use a Grignard to create any old aldehyde or ketone that we want. What will we start with? Does anybody remember? So this was kind of a weird one because Grignards react with the aldehydes and ketones. So to have one as a product of a Grignard reaction, we started with a very special functional group, and that would be a nitrile. Right? So a cyano group will react with the Grignard and create a ketone or aldehyde.
I have a question.
Yeah.
Would that not just react again and form?
No, because, and this is a very subtle point, but if you remember, you have these two steps in any Grignard reaction. You have it where you react it with the nucleophile, and then you follow up with an acidic workup. And actually, after that first step, what you get is an enamine. And it isn't until you follow that up with that acid from the second step that it converts it into ketone or aldehyde. And at that point, after you've added the acid, you've already like killed all bit of Grignard reagent that was in that pot.
Oh yeah, you mentioned that. Okay.
Yeah, yeah, it's a very subtle whatever, but yeah, nonetheless, that's sort of the why you don't have it reacting with itself, more or less. Okay, so these are just these two different organometallic methods that we had of creating a Grignard or aldehyde, right? So creating a ketone or aldehyde. So when we're creating our little summary reaction wheel, we want to make sure to add those two to it, in addition to everything that was kind of nicely listed at the beginning of chapter 19. Okay, we're sort of crunched for time. I got a meeting at 2, so I need to like make sure that we're sort of sticking to a schedule here. So I'm going to try to just go through the most important things that I think need to be reminded of. One of which is something that I think is just really easy to overlook because we haven't talked about it very much in forever. And that's just like what happens with the ketone or aldehyde when you react it with water. So everybody take a second and see if you can give me the product of this reaction. It's kind of not, I don't know. It's something that's easily forgettable, I feel.
Didn't you say a ketone?
Ketone or aldehyde.
Okay.
And this time we're going to use formaldehyde for a particular, because I'm going to make a particular point about this, but it could be anything. You could have any R group instead of hydrogen there. Does anybody remember what we get?
It makes a diol, doesn't it?
Yeah, so we call it a hydrate, but yes. So in this case, what happens is that a water will react and stick two oxygens in the place of that, onto that carbonyl carbon. And again, these hydrogens can sort of be anything, and this reaction will happen. The reason that I picked formaldehyde in particular was because formaldehyde is literally the only aldehyde in this case where the reaction favors the products. For most ketones or aldehydes, it actually favors the reactants, but this reaction is still happening, okay? And it seems like such a stupid subtle point, but the ACS kind of loves these types of things. Remember, instead of using water, I could have also used any old alcohol. And I would have had the same thing, except for instead of putting OH groups on there, I'd be putting OR groups on there. Okay, but these are like the very first reaction that we learned about in our ketones and aldehydes chapter, and we just don't want to dump it from our memory. Okay. Now, just to kind of take everybody back to this particular chapter, this was an incredibly mechanism-heavy chapter, okay? So what we learned about was, in all of these reactions, every single one of these reactions, what's our electrophile when we're talking about an aldehyde or ketone?
The electrophile? It's the,
Yeah, what's going to be the electrophile in a reaction between any one of these and an aldehyde or ketone?
the carbonyl carbonate.
The carbonyl carbon, right? So this chapter was incredibly mechanism heavy. We learned about a bunch of different nucleophiles, but they all kind of fell into this same category. And in every single one of these reactions, your carbonyl carbon is the electrophile. And then you have these various nucleophiles, right, with their pairs of electrons going on. We kind of classified them as being acidic, neutral, or basic. Remember, in an acidic mechanism, everything always has either a positive charge or it's neutral. In a basic mechanism, everything always has a negative charge or it's neutral. And then specifically when nitrogen's involved, you have these neutral mechanisms where you can have both positive and negative charges. Okay, but this chapter was 90% of this chapter can be summarized as, here's an aldehyde or ketone. If we're in acidic conditions, what happens first?
The
Oxygen gets protonated.
Oxygen gets protonated. So the very first step under acidic conditions is always to protonate that oxygen. And then you have your nucleophile attacking the carbonyl carbon. That kicks that pair of electrons up. And under basic, and the whole reason why we have to protonate that oxygen first is because if we didn't, when that pair of electrons got kicked up, it would be a negative charge. Right? So we have to protonate that oxygen first. That will give us this tetrahedral intermediate, and go from there to kick off that oxygen and replace it with whatever group is being replaced with. And then if we had instead basic conditions, first step, nucleophilic attack, giving us a negatively charged intermediate. All right, so I'm going to click over to Unit 4 here in 1 second. The last thing I just wanted to remind you guys about this chapter is that there was 2 additional reactions that we learned, the Wittig and the Bay-Villager. So just to quickly summarize real quick. Remember, a Wittig uses this big, ugly compound here, and it just substitutes the oxygen on the aldehyde or ketone, or whatever the back half of this elide is. You're replacing a double bonded oxygen with a double bonded carbon.
For that one, was it stuck to being a carbon with 2 hydrogens, or could we have R groups attached to that carbon?
You can have R groups attached to that carbon. The one caveat of this is because If you're doing like retrosynthesis, right, either half of this, the green half or the blue half, could have started out as the elide. You want the smaller one to be attached to the phosphorus. That was kind of like the caveat of these particular reactions. Whatever that smaller fragment is, that should be, and this is what this guy here is, the elide. The smaller fragment should be the one attached to the phosphorus. Okay, but again, sort of just broad summary of these Wittig reactions. You have a double bonded oxygen being replaced with a double bonded carbon. The Bayer-Villiger, well, is when we have an aldehyde or ketone, we react it with a peroxy acid. And what peroxides tend to do, and it does in this particular case as well, is insert an oxygen in between an existing carbon-carbon bond. Right? And since that one of those carbons is a carbonyl carbon, you're going to create either an ester or a carboxylic acid from it. Okay, so just remember those last two, the like bulk of that chapter can be summarized as nucleophile attacking carbonyl carbon. And then there were these two little additional reactions that we tacked on to the end of that chapter as well. Okay, cool. All right, so now let's move on